Hi, in this video, I will explain how can we estimate the regression models manually in R. Uh, Before doing the calculations manually, let me first explain how can we express the regression model in terms of matrices. So I take the simplest case where we have only one independent variable x. So in this case, the regression model can be expressed as y equals to beta 0 plus beta 1 times x plus epsilon. This is an error term in the regression model. So now for each data observation, we can write the regression model as simply by keeping the observations of y and x. For instance, for the first observation of y and x, we can write the regression model as y1 equals to beta 0 plus beta 1 x1 plus epsilon 1. For the second data observation, we can write y2 equals to beta 0 plus beta 1 x2 plus epsilon 2. And in this way, we can continue. And for the last observation, we can write yn equals beta 0 plus beta 1 xn plus epsilon n. So we can write this in compact form by simply keeping the values of y in y vector, and by compacting this expression into the matrices of independent variable and the column 1. So simply the first column is 1 1 1, and the second column is our independent variable with its observations, and then the beta matrix or the beta vector. So if we multiply these two matrices, or this matrices and this vector, we will get the same result. So in this way, we can divide this expression into a product of a matrix of independent variable and ones and the vector of our parameters. Then plus we can separate the observation of the error terms into a separate vector, and we can name this column as y vector, this as x matrix, and this as the vector of parameters beta, and this vector as the vector of error term. So this expression works for whatever number of independent variables. If we have for instance two independent variable, other things will be same, and the x matrix will be now the matrix in which the first column is 1 1 1, and the second column is our observation of first independent variable, the third column will be the observation of the second independent variable. So for any number of independent variable, the matrix representation will be the same. So now we can estimate the beta vector. We can estimate the beta vector in matrix form by simply using the method of least squares. In the method of least square, we minimize the sum of square deviations. So, or we simply minimize the sum of the squared error terms. So we can define the sum of squared error terms as simply the product of the error vector times the transpose of error vector. So if we multiply the error vector with this transpose, we get simply the sum of the squared error terms. So the error term can be calculated as simply the difference between y vector and the xb matrix. xb matrix. If or y vector and the xb vector, if we multiply these two, it will be a vector. So if we subtract xb vector from y, we will get the vector of error term. So we can put y minus xb instead of e vector, and we can minimize this by using our standard calculus. So I wouldn't go in detail how to calculate the derivative of this expression, but if we simplify, the final result will be the beta vector equals to the inverse of x transpose times x. So we first multiply x transpose and x, and then we'll find its inverse times x transpose times y. So this formula is used in all statistical softwares to estimate the coefficients of the regression model, and we will do the same in R. So now let me move to the R studio, in which I have written the codes already. I have put this file in the description of this video. You can import the data set from website, so there is no need of downloading data and putting it in your computer folder. So let me first download the data set. If I click run in this command, the data set will be downloaded from the website to your RStudio environment. So our goal here is to first find the beta vector by simply multiplying the x transpose and x and finding its inverse, and then multiplying the result by x transpose times y. So first we will define the x vector and y vector. The y vector is simply the vector of independent variable. So let us suppose that our dependent variable, suppose dependent variable is wage rate, and we define the y vector to be wage rate. The x vector, as we saw before, the x vector or the x matrix, the x matrix is a matrix in which the first column will be 1 1 and then the values of the independent variables. So suppose that we have in 3 independent variables: years education, experience, and ASVABC, which is a cognitive ability score. So 3 independent variables and then preceded by the ones. So we combined ones with the values of these 3 independent variables to define the X matrix. So if I hit Control and Enter, it will define a X matrix which has ones in the first column, and then the values of years education in the second column, experience in the third column, and ASVABC in the fourth column. We can look at the object y. So y simply consists of the values of wage rate, and the x matrix consists of the x matrix. The x matrix consists of 4 columns. The first column is simply ones. The second column is the values of years education. The third column is the value of experience, and the fourth column is the value of the cognitive ability score. So after defining the X matrix and Y vector, now we go ahead. So our formula is X transpose X inverse times X transpose Y. So we can go part by part, or we can write the formula in a single line of code. So I will first go part by part. So I will first define the transpose of X. The transpose of X can be calculated in R by the T function. The T function T inside parenthesis X defines the transpose of X matrix. So I name it by XT. So xt is given simply by the transpose of x. Xt is a matrix which is a transpose of X matrix. Then I will multiply X transpose and X to multiply matrices. The function in R, or the function or the procedure in R is to keep percentage, asterisk, and percentage sign. So xt percentage, asterisk, and percentage times x multiplies these 2 matrices. So xt is the transpose of x, and x is a matrix we define. To multiply these 2 matrices, we keep percent, asterisk, and percent sign between them. So this multiplies these 2 matrices and saves them in A. So A is a matrix which is defined by X transpose times X. So now then we define the second part, which is X transpose times Y. So X transpose times means percent, asterisk, percent times Y, and we save this in B. Then we find the inverse of x transpose times x. So we have saved x transpose times x in A. So to find the inverse of x transpose x, we simply can find the inverse of A. So to find the inverse of a matrix, the function in R is solve. So solve A finds the inverse of A. So we run this command. This now saves the inverse matrix of A in A inverse. And finally, we have defined this and named it in B. We defined x transpose x and named A, and then we found its inverse and named it as A inverse. Our final command would be to multiply these two parts, the later part with the previous part. The previous part is A inverse, the later part is B. So finally we multiply again the two parts, A inverse times B. So, and we save this as beta 1. So now the beta 1 is our beta matrix. We can simply look at what is inside beta 1. So the beta 1 has the regression coefficients. So constant is 29.3, the coefficients of years education is 2.04, experience is 0.45, and the coefficient of ASB ABC is 0.26. So we can simply transpose this. We can simply transpose this by t beta 1, and we can even fix the number of digits. So this will transpose the beta vector and keep it in a row. So now we can check whether our estimations are correct or not with the inbuilt LM function in R. So the inbuilt LM function estimates the OLS regression. So I save the results of the inbuilt function in the object called model, which is defined by the linear regression with dependent variable wage rate and independent variables years education, experience, and ASB ABC. So I run this model and I ask R to show its coefficients or the coefficients of model, the regression model. So again, I first print the beta that I estimated manually, and then I ask R to print the coefficients of the model which have been estimated by the inbuilt LM function. So if we look at these two set of coefficients, we see that the coefficients are exactly same. The only difference is the number of digits. The number of digits from the model are 7, whereas the number of digits in our manual estimation have been smaller. So in this way, we can manually estimate the regression coefficients by simply using the matrix formula as x transpose x inverse times x transpose y. So this whole line of command can be written in a single line that I have written here in 21. So 21, I have written the whole formula in a single line. So the first part is transpose x times x. So this is inverse of transpose x times x. Solve means inverse. Inverse of x transpose times x times x transpose times y. So if I run this and if I ask R to print its coefficients, the coefficients are same as before. So with a single command, single line of command, we can find the estimates of the parameter of regression model, and we can cross-check it with the built-in LM function. So the next step is to find the predicted value. The predicted value can simply be found as the product of the beta vector with the x matrices. So we save the predicted value in the name of y hat. So y hat is given by the x matrix multiplied by the beta matrix. So if we multiply this two, it will give the estimated value of y. Now the residual term, the estimates of the residuals or estimated residuals can simply be found by subtracting the estimated y from the actual y vector. So let me rename it as u hat. U hat is the estimated residual by simply subtracting the estimated y from actual y. So now I can define the residual sum of square, which is the difference. The residual sum of square is simply the difference of actual y and estimated y squared and then summed up. So the residual sum of square is simply defined by the residual square. Residual square is now u hat and summed up. So if I run this, it will define the residual sum of square, which is sometimes called the error sum of square. So this can simply be defined as u hat transpose times u hat transpose times u hat. It will also give the same number. So this is u hat transpose times u hat. It will also provide us the same number. So the first one, RSS, has been calculated as summation e squared or summation residual squared, and the second one is simply A transpose times E. So both yield us the same value of the residual sum of square. So this residual sum of square will be further used while calculating R square manually, and it will also be used while calculating the variance covariance matrix and the standard error of the regression line or standard error of the error term. So we'll now move to how to estimate or how to calculate the R squared manually in R. So R squared is simply be defined by the formula that we study in our statistics course, which is 1 minus the unexplained variation divided by total variation. We defined the unexplained variation by RSS, and we have defined it already, and we can now define the total variation or the total sum of square by simply using the formula summation y minus y bar square. So summation is denoted by sum function in R, and then y is y's rate and y bar is the mean value of y, in our case the mean value of y is mean value of y's rate. So the mean function in R calculates the mean value. So we simply write here y minus mean of y squared and then summed. So this will define the total variation in R, and now we can define the R squared as 1 minus unexplained variation divided by total variation, and we can look the value of R squared, and it's 0.2197. So what this implies is that 21.97% variation in the wage rate is explained by our independent variables. We can even round the value of R squared by using the round function, and comma 3 rounds it to 3 digits. So now we move to the next one, how to calculate the standard error of regression manually in R. So the standard error of regression can be simply defined as the square root of RSS divided by n minus the number of parameters. So we first define n as the total sample size, and this can be defined as n equals to number of row in our data file. So number of row and the name of the data file defines the total number of observation, and in our case it is 540. So now we can find this standard error of regression line as the square root of RSS divided by n minus the number of parameters. So the number of parameters in our case are 4 because there are 3 independent variable and one constant of the regression model. So in our beta hat vector, there were 4 parameters estimated. So the number of parameters is 4. And while defining the standard error of regression, we divide the residual sum of square, or we divide the unexplained variation by n minus the number of parameters, which in our case is 4. We can simply write 4 here, but it can also be found from the number of columns in our x vector. The number of columns in our x vector is 4. So this is simply n minus 4. 4 is the number of parameters in our regression model. So if I run this, it calculates the standard error of the regression line, and we can see that it's the 12.76. And now at this stage we can just compare this with the inbuilt function. So if we summary the inbuilt results, or if we summarize the results from the inbuilt function, we have saved the regression results from the inbuilt function in the object called model. If I summarize this, look here, the R square value is 0.2198. The R squared value is 0.2198. The R squared found by us was 0.21979. So if we round this, it will be the same. Now the next standard error we found was 12.76, and the standard error from the inbuilt function was 12.77. So again, the rounding error only, the numbers are exactly the same. Okay, we will next move to the variance covariance matrix, from which we will find the standard error of our coefficients or our parameters. To find the variance covariance matrix, the formula is the variance of error terms times the inverse of x transpose x. So we have already found the inverse of x transpose x. So we can use that. For instance, we can use the x transpose x inverse, which we have calculated and saved as A inverse, or we can again calculate the transpose of x and find its inverse. So the formula here is the variance covariance matrix is the variance of error term times the inverse of x transpose x matrix. So I have written the codes for this formula here. The variance has been calculated by this command line. So this variance is nothing but a square of the standard error of regression. So we can just square the standard error of regression, which is also the standard error of the error term, which is 163. Or we can find the variance of the error term as simply unexplained variation divided by n minus the number of parameters. In our case, it is n minus 4. So we can run this command, and we can see that the number from this formula is again 163. So after finding the variance of error term, we define the variance covariance matrix as variance of error term times the inverse of x transpose times x. So as I said before, we can find x transpose in a separate line of command, then multiply x transpose by x in a separate line, and finally find its inverse. Or we can do all the three functions in the same line. We first find the transpose of x, then multiply transpose of x by x, and then finally find its inverse and then multiply by the variance of error term. This calculates the variance covariance matrix. So we can see the variance covariance matrix as a 4 by 4 matrix in this case. Since we have four parameters, there will be 4 by 4 variance covariance matrix. So the standard error of the regression parameters or the standard error of the regression coefficients are nothing but the square root of the diagonal elements in this variance covariance matrix. So we can extract these diagonal elements and find the standard deviation simply by the function is squared and then diagonal of the variance covariance matrix, which we have defined in the line above. So we first extract the diagonal element from this matrix, and then find the square root and save them in the vector standard error. So the standard error vector saves the standard error of the regression coefficients, which have been extracted from the variance covariance matrix and by finding a square root of them. So now we can combine the coefficient vector that we have found and the standard error that we have just found into a matrix by the cbind command. And the cbind command combines the beta 1, which is a vector of our coefficient, and standard error, which is a vector of the standard error of the regression coefficients that we've just found, into a single vector or single matrix. And we can compare whether our standard errors are correct or not by comparing this with the result from the inbuilt LM function. We have already estimated the regression model from the LM function and saved it in model object. We can summarize our model object and we can now compare. We can now compare our coefficients with the coefficients from the built-in function and our standard errors, the standard error that we have found with the standard error from the inbuilt function. We can see that all the numbers are exactly same except the rounding digits. So in this way we can find the model coefficients, we can find the R square, we can find the standard error of the coefficients manually. So after finding this standard errors, we can find the t ratios, we can find the probabilities corresponding to the t ratio. So to find the t ratio, we simply divide the beta vector by standard error. So how we define t for a coefficient is simply our coefficient, our beta coefficient for a variable divided by standard error of the coefficient. So in this case, we find the t ratios for all of the parameters at a time by dividing the beta 1 vector divided by the vector of standard error we have found. So if we divide the betas by the standard errors and save them in t object, and if we ask R to show what is inside t, it will show the t ratios. Again, we can compare this t ratio from the results of the inbuilt function, and we see that the results are exactly the same. Now, even we can find the probabilities in R. To find the probability corresponding to t ratio, the corresponding function is pt. For instance, if we want to find the probability associated with the t value of 1.96 and the degree of freedom n minus 1, which is 540 minus 1, in this case 539. So the relevant command is, so you can delete this is simply the name. So the relevant command is 1 minus pt. Pt means probability t, then t value and the degree of freedom. So if we enter this, the corresponding probability is 0.025. So for instance, if we want to find the probability with the t value 5 and the degree of freedom, for instance, a little bit lower, 100, the probability associated with this number is very small. So in our case, the t ratio, for instance, let me try the t ratio of 7.00 to find the probability associated with t ratio. We can simply write this function 1 minus pt. Sorry, this is 1 minus pt, then the t ratio, which is 7.000, then degree of freedom in this case is n minus 1, which is 539. So the t value is very small, 3.82. This number is very small. The 0.11 zeros followed by 382, so it is almost 0. So now compare this with the probability from the inbuilt function, which is also a very small number. So if we round these probabilities, to 4 digits, its value is 0. So now we will not find the probabilities one by one, but we will find the probabilities at a time. So for this we'll write the t vector here, which is the vector of t ratio that we have found, and we will round the probability. So we'll first use the round function, then 1 minus pt, then the t vector, then degree of freedom equals to a number of row minus 1. So you can write just 540 minus 1, or you can just write 539 in this case. But I have put the codes so that you can use it in other cases also. For instance, you can change the X matrix, you can change one independent variable, you can remove one independent variable, and this formula works for that too. So in this case, I have just write the function n row of x, which is 540 in this case, 540 minus 1, and this 7 is the digit for rounding. So since we have used the round function, we should specify the number of digits. So if I run this and look what is saved inside the probability, there is one problem with the first one. Why this is a problem is that from the inbuilt function, the probability was very low, almost 0, but in our case the probability appears to be 1. So this can be fixed by ignoring the minus sign with the t ratio, ignoring the minus sign with the first t ratio, and this can be done in R by using the absolute value function. And in the next line of code, I have simply taken the absolute value of the t ratio, and other things are same, and I run this, and now the probabilities are here. Now we can compare these probabilities with the probabilities from our model. Again, I summarize the model from the inbuilt command and look at the probability. The first two probabilities are almost 0, 0.11 zeros followed by 2, this is 0.10 zeros followed by 2, and this is 0.11 zeros followed by, so these two probabilities are almost 0. So This is 0.00569 and this is 0.00370. Now we compare this with our probabilities. So our probabilities are saved under the probability object. So the first two numbers are almost 0, and this is almost same with the model, and the other two probabilities are same to the third digit and differs marginally. So if we round the probabilities to two decimal places, all the probabilities are 0, and in this case also the probabilities are 0. So in this way, now we have come up to finding the coefficient vector, then standard error, and the two ratios and probability. Now we can summarize them. We can summarize them simply by combining them by the cbind function. So we first write the coefficient vector. The name of the coefficient vector is beta 1. Then standard error. So the name is standard error. And then we will save the t ratio, and the name of the object is t, and then probability. So if we run this, there will be 4 columns. The first column is the coefficient vector, second one is standard error, third one is t ratio, and the fourth one is probability. And you can compare this number with the results from the estimated model from the inbuilt function. Finally, I will move to the ANOVA test. The ANOVA test can be simply done in R from the explained and unexplained variation ratio. So now first we define the explained sum of square. The explained sum of square is the difference between total variation TSS minus RSS. So we have defined TSS and RSS while calculating the R squared. So TSS is total variation and RSS is unexplained variation. So since we have these two values, we can define the explained sum of square as the difference between them. And then we define the mean sum of square. As you can see in the ANOVA table, we define the mean sum square of explained variation, mean sum square of residual variation, and we define f as the ratio of mean sum square of explained variation divided by mean sum square of unexplained variation. Okay. We first define the MSE. MSE is mean sum squared of explained variation, which is simply defined by the explained variation divided by its degree of freedom. So its degree of freedom is simply the number of parameter minus 1. So number of parameters means the number of coefficient. In our case, it is 4 minus 1 is 3. So in our case, it is 3. So the mean sum square of unexplained variation is simply given by the unexplained variation divided by its degree of freedom. Its degree of freedom is simply the number of observation minus number of parameter. Okay, number of observation minus number of parameter. So in our case, the number of observation is 540 minus number of parameters is 4. So this is 536. Okay. After defining the MSE and MSR, we define the F ratio, and the F ratio is 50.33. So we can compare this ratio with the results from our estimated model from the inbuilt function. So the F ratio from the inbuilt command is 50.33, and from our calculation it is again 50.33, so exact same results. Now finally we calculate the probability of F. The probability of F can be found by using the PF function in R. In PF function we simply define the value of F first, the value of F ratio, then the degree of freedom per the numerator and the degree of freedom per the denominator. So in our case, for instance, 1 minus PF, the F value was 50.3319, comma, the degree of freedom for the numerator is a number of parameter minus 1. Number of parameter minus 1. Number of parameter minus 1 is 4. 4 minus 1. 4 minus 1 is 3. And the number of freedom per the denominator is n minus the number of parameter, which is 540 minus 4, which is 536. So if we find the F value, if we run this command, the F value 0. So this can be done by simply writing it in the form of formula. So there is no need of writing the numbers. So writing in the form of function will help you to calculate the probability of F. If you add independent variable inside the X matrix, or if you remove any variables, if you change any variable inside the X matrix, if you change the number of observation, if you delete some observation, the formula will work. Okay, now if you calculate the probability, it is 0. So now we can compare the F value and its probability with the results from the inbuilt function. So the F statistics from the inbuilt function is 50.33, which is same as our results, and the degree of freedom for the numerator is 3 and the degree of freedom for the denominator is 536, as I just said, and the probability value is almost 0. This number is 0.15 zeros followed by 22, which is almost 0. So in this way we can calculate all the statistics that is reported by the LM function, in R manually, and can understand its part and persons one by one. Thank you very much for watching this video. In the next video I will explain you about how to calculate the residual diagnostic statistics, such as the Lagrange multiplier test, multicollinearity test, and other tests.